often highly specialized.
This is one plant that has met the challenge of Haleakala. It's a silver sword, Agariciphium samwichense, and it grows only here. In fact, at one time, silver swords covered the floor of the crater, but now, perhaps because of the grazing and the damage from goats and people, they're very rare, so they are rather remarkable, unique plants. And it's only because this has been declared a wilderness area and protected by the US Park Service that, in fact, silver swords survive at all. So, what is the environment that this rather special plant has to cope with? Well, there is indeed a shortage of water. There's a real problem here. Rainfall is pretty low, probably about 15 inches here. But in addition, the soil is this raw volcanic lava, very free-draining, very unstable. It doesn't retain any water. So what rain there is drains away very quickly. And in addition, there are strong, drying winds for much of the time and very bright sunlight. So this tends to heat up the plant, and all these conditions combine to create conditions where there is very strong transpiration, when there isn't much water left for the plant to transpire. So how do silver swords adapt to these conditions? What features of them do you think combine to make them survive in this very harsh environment? Well, if you look at the leaves, one of the most striking things about them is this covering of silvery hairs, which gives the plant its name. Now, we don't know precisely the role of these hairs because the physiological work that's necessary hasn't been done. But from work with other plants, it seems that hairs like this act mainly to reflect the light. And in reflecting light, quite a lot of it, it seems to keep the temperature of the plant down. So that reduces the temperature gradient from the plant to the air, and that reduces or helps to reduce the rate of transpiration. There are other complicating factors. The hairs can do other things. They increase the boundary layer, for instance. But the main role here seems to be light reflectance and reduction of plant temperature, which also keeps the temperature in the range optimal for photosynthesis. If you look at the plant's general habit, well, this rosette form, which is a very characteristic feature of silver swords, possibly related to the cold that it experiences, because it can be pretty cold here. It can get down to freezing at night and even snow in winter. And the other interesting thing about the leaves of the silver sword is that if we take a section of one, then you might be able to see that they store water. It's held there as a solution of pectic substances in the intracellular spaces. So far as we know, this stored water isn't used during the normal life of the plant. But there's one very special exception to this. When this happens, when the silver sword flowers, which it does after perhaps 7 to 20 years' growth, all the water in the leaves is used up. The leaves wilt, they fall down like this, which incidentally indicates that the water in them does help to maintain the stiffness of the leaves. And the water is used, apparently, in one great burst, so that the plant can put on a great flowering show, and then it dies.
Plants in more moist environments than the silver sword usually don't store water, and nor do they have such specialized adaptations for conserving water. On the contrary, trees like these may lose over 100 litres of water a day. It's lost by transpiration from the leaves. We can show transpiration and measure it with a simple technique. Dr. John Milburn, Glasgow University.
An hour ago, this leaf was enclosed in a plastic bag. We have good evidence of transpiration from the fact that droplets of water have collected on the walls of the bag. The difficulty is we cannot use a technique like this to measure transpiration because it interferes with the rate of water loss itself. With a potted plant like this, by far the best and simplest method to measure transpiration is to weigh the whole plant. An hour ago, this plant was placed on the balance and it was zeroed. Now it indicates that the plant has lost 2.29 grams of water. So we're measuring transpiration as a change in weight per unit time. Some leaves can lose up to 3 times their own fresh weight per hour. The problem to the plant is how to replenish this large amount of water lost in transpiration.
Well,
Well, we all know how most land plants obtain water from the soil via their roots. Using time-lapse photography, we can see how a root exploits the soil by continually penetrating into new regions. As it does so, the root makes intimate contact with soil particles and their surrounding film of water. But this is possible only if root cells are turgid, stiffened and inflated with water. So why does water enter root cells, and how and why does it travel through the plant? Well, this has been explained in terms of gradients of water potential, delta psi. Water flows from regions of higher to those of lower water potential down the gradient, and psi, which is measured in units of pressure, is usually highest in the soil. It falls progressively from roots to shoots through the plant and is lowest of all in the atmosphere.
I can explain movement of water along gradients of water potential into cells using this simple model. The yellow balloon represents the protoplast of the cell containing the vacuole. On account of the solutes in the vacuole, water potential is lowered inside the cell, and so water will enter from outside, where the water is at a higher water potential, and produce pressurization. The protoplast would in due course burst in this situation, but it's prevented from doing so by this net that represents the cell wall. And as we pump, you will see that the pressure increases rapidly as the protoplast meets the cell wall. This produces a condition of turgor and accounts for the support given to plant cells. When a cell becomes fully turgid, it can no longer absorb any water, but most plant cells in the normal situation are only partly turgid. This accounts for the curious paradox that though the cell is pressurized, it is nonetheless exerting suction on water in cells round about it, and this accounts for the mechanism by which water is drawn into the cells. If a cell loses quite a lot of water, it wilts, and in this condition, it exerts the maximum degree of suction.
In these leaf cells under the microscope, we can induce a condition similar to wilting. They've been put in a strong salt solution so that gradually they become dehydrated. If you watch the purple-coloured cells, their protoplasts contract and pull away from the cell wall. These cells are becoming plasmalized. Their water potential is falling as their turgor falls and their solute concentrations rise. In a root, small differences in turgor and solute levels allow water to move from cell to cell via the protoplasts. But water may also follow a path of lower resistance along the cell walls until it reaches the endodermis. Here, water must enter the protoplasts because endodermal cell walls have a waterproof layer, here stained red. The waterproof layer starts off as a thin band, the Casparian strip. Here it's seen in an electron micrograph through the endodermal wall. Laid down on top are secondary layers of thickening. Once through this endodermal barrier, water eventually reaches the central xylem elements. These are dead cells with lignified walls that link up to form long hollow tubes, xylem vessels. Through these, water travels from the root to the stem and leaves. But how exactly is water lifted up xylem, right to the tops of tall trees? Is it pushed up by the roots or pulled up by the shoots? Well, let's consider first the evidence for pushing forces. About 3 hours ago, I cut the leaf off this arum plant, and that drop of fluid there is xylem sap that's exuded, it's bled from the cut stump. Now, that must have been pushed up by the roots because there was no leaf there, no shoot to do any pushing. This root pressure, as it's called, arises because plant roots can actively accumulate ions. And without going too deeply into the mechanism, it's rather as though the whole root with its thousands of cells behaves like a single giant cell, a single osmotic unit.
It accumulates ions, lowering the internal water potential, so water is drawn in from the soil and can pass on into the xylem. This drop of fluid here on the tip of the leaf, now that is caused by root pressure forcing water out of the leaf through special areas of cells. It's called guttation. You may have noticed plants covered with droplets of fluid like that, especially in the early mornings when it's cold, and thought perhaps that it was dew condensed from the atmosphere. In fact, most dew that people see is guttation fluid exuded by the plants. But root pressure doesn't occur under all conditions, and even when it does, it's usually inadequate to account for the transpiration losses as we can measure them. All the evidence that we have suggests that a pull, a suction exerted by the transpiring leaves, is the major force involved in lifting water up the xylem. And I can demonstrate this pull using a simple device. This is a potometer. It's quite a simple gadget, and all I've done was to cut this chute underwater and then attach it to this system of tubing, which is all filled with water to which I've added a dye, so it's coloured. And there's now a continuous column, you see there. And as the chute transpires and loses water, so the meniscus of coloured water is sucked along that tube there. So it literally gives you a measure of the rate of sucking, the rate of drinking. Of course, the amount of water that a little chute like this can suck up is quite small. But when you think how much a big tree can suck, well, then it becomes an enormous quantity. And the question arises as to how this suction force is actually generated in the xylem. Well, it was suggested that xylem vessels can act like capillary tubes.
Capillary tubes can develop suction, but how is this? Water tends to stick to glass and creep along it. This stickiness is caused by hydrogen bonding, which also holds the water together. The net effect of this is that water tends to climb up narrow glass tubes. And wooden tubes behave in the same way. These capillaries correspond to the widest xylem vessels. And the water rises only a little in them, showing a small degree of suction. Even in the narrow tube, the suction is trivial in comparison with the needs of the plant. Nevertheless, in the porous walls of the living cells, there are very fine capillaries which can generate much more suction. This can be explained using a model. I call this my porous pot model. It consists of a porous pot which contains many very fine capillaries corresponding to the fine capillaries in the cell walls of the living mesophyll cells. It's attached to a tube here which is full of water and equivalent to the xylem in the plant. And at this end, there's a gauge registering suction. As water is lost, suction is generated, which registers on this gauge. This simple model can generate a suction equivalent to a capillary tube drawing water 10 meters vertically. The question that can be asked is, why does a plant not draw all its water through capillaries as fine as this? The answer is simple: friction. The friction would be far too great. The plant needs to draw water through the wider tubes of the xylem because it's much easier, and that's the reason that it's constructed the way it is. So this means that the wide tubes of the xylem must withstand considerable suction, even greater suction, and I can best show this by looking at the tubes of an intact plant. Here is an intact plant, and what I've done is to bare the xylem by peeling away the bark from the outside. I've applied a film of grease over the surface because I'm going to put on here coloured fluid, ink, onto the surface. What I'm now going to do is to prick through the droplet of ink into the xylem. The ink has been drawn vigorously into the plant, indicating a vigorous suction. Now, if the liquid were under positive pressure, the sap would squirt out.
Thickening in xylem walls, such as these spirals of lignin, allow the vessels to withstand strong suction forces without collapsing. In mature xylem, a pattern of reticulate thickening is more common, and this gives even greater strength. But there are always thinner areas in the walls, pits. These show up as dark holes in the right-hand vessel of this scanning electron micrograph. Through these pits, water can move from one vessel to the next, both sideways and vertically up the plant.
So what sort of pressures can xylem vessels withstand before they start to collapse? How can you measure the suction in xylem? One way is using a machine like this, which is called a Scholander bomb, after its inventor. This chamber here can be pressurized with compressed air, and what I've done is to put a leaf in the chamber with its petiole coming through a bung, so it's airtight in the lid here, and the cut end pokes out into the air. Now, Scholander argued that when xylem under tension is cut, then air is going to be sucked in, and you saw this sort of thing happening with the dye earlier. The more negative the pressure inside, the more air gets sucked in. Now, with a system like this, what happens is that the air inside there, the pressure, compresses the cells until the xylem vessels are once more refilled with water. And then the positive pressure there is equal, but of opposite sign, to the negative pressure in the xylem. I can illustrate the principle with these sponges. When you've got a wrung-out sponge, it takes quite a hard squeeze, a lot of force, before water starts to drip out. But with a wet sponge, only a slight pressure, and out pours the water. Okay, now the bomb's set up and ready to go. Well, I hope not literally, so I'll put on the safety spectacles and we'll pressurize the chamber gently as possible, keeping a close eye on the cut stump of the plant. Right. Now, water has exuded from the xylem. I've cut off the airflow, and the pressure needed to refill that xylem and cause it to exude from the stump, according to the dial here, is about 3.5 bars. That's 0.35 megapascals in SI units. It's safe to take these off now. Now, a suction of that size is enough to draw water up to a height of about 35 meters or so. But suctions have been recorded sufficiently great to draw water up about 450 meters, which is really rather remarkable. With forces of this size, it means that the columns of water in the xylem are under tremendous stretching forces. And if they break, then water flow along the xylem will stop. So do the columns of water in xylem ever break?
The noise we've been listening to is caused by the breakdown of the system. The phenomenon is known as cavitation, and it arises because the water in the xylem tubes has been pulled too hard and snaps. This is a very violent event. Energy is released and produces a sort of small earthquake. Now, the way this is detected is that from this leaf, it's impaled on a microphone which detects the vibrations. This lamp merely augments transpiration to increase the rate of clicking. The shock waves are translated into electricity, amplified here, and we listen to them on the headphones. Now, when cavitation occurs, it's extremely damaging for the plant because it has bubbles in the tubes that should be used to conduct water. Now, it may be that cavitation damage in the form of bubbles can be removed by root pressure, which squeezes the bubbles out of existence. If this is so, then curiously, root pressure has a role to play in xylem conduction of sap, but not the direct one that was at first thought, rather an indirect repair system.
Xylem pits are also an important defence against cavitation. This bordered pit can close up to stop the spread of air bubbles. So one vessel may be sacrificed while others remain functional. Water supply can be disrupted in other ways too. These white balloon-like structures protruding through the pits are gummy secretions called tyloses. They block up the vessels and are produced in response to injury or infection. In this case, it was caused by a fungus, Ceratocystis ulmi, which infects elm trees and is carried by this bark beetle. The fungus spreads in the outer layers of the bark and causes Dutch elm disease. Tyloses, here seen as a ring of dark spots, are formed in the diseased elms. They can completely block up all the functional vessels in the outer layers of wood. When this happens, the tree effectively cuts off its own water supply. The leaves wilt and eventually the whole tree dies.
Water is vital for plants to survive. And even in Britain, many plants have to protect themselves against losing too much water. Most of the water is lost as vapour through stomatal pores on the leaf surface. And a lot of the devices for protecting the plants against excess water loss involve covering up and shielding these pores in some way.
This is what a typical stomatal pore looks like under the microscope. The pore is surrounded by two sausage-shaped guard cells. They can change shape and alter the diameter of the pore so that it can be open or closed. With marram grass, a xerophyte able to grow on dry and exposed sand dunes, the stomata are protected in deep grooves on the lower surface of the leaf. When it's really dry, the leaf rolls up. This cross-section shows how a layer of air is trapped in this way around the stomata. Hairs on the leaf surface may also help to retain a layer of still air, and insulating hairs are very common in xerophytes. This desert xerophyte is unusual because hairs occur actually in the stomatal pores.
Since the special feature of stomata is that the pores can be opened and closed, why don't plants simply keep them shut all the time? Well, most can't do this because they need open stomatal pores for at least part of the day for gas exchange, particularly for the entry of CO2 in photosynthesis. But there's one group of plants, known as the CAM, or CAM plants, which don't need to do this. They close their stomatal pores during the day when the transpiration losses are high, and they open them only at night when it's cooler and more humid and losses are a lot lower. We'll be talking about the consequences of this for photosynthesis in a later program.